All right, you guys, here are a few more practice problems on Lagrange error bound. Yeah. Let me get my color going here again. So let's remember, yeah, you like my excitement there? Let's remember that if it's an alternating series and the series converges, which is going to be almost all the time when you're asked about these error bounds, it's going to be a series that's alternating and converging. So you're going to use the next term. So if you're given asked for the error of a third degree term, you go to the fourth degree term. Note whether they're talking about a fourth term or a fourth degree term, because a fourth degree term could actually be a fifth term. So just be careful on that. If the series is not alternating, we go to this thing that we were talking about in the last video. Okay. Okay. So let's do this next one. What I would like you to do actually is, why don't you guys try it first, and then, so pause this video and then come back to it and see how you did. Okay, so I'm not going to pause, but I'm going to ask you to pause. All right. So x cosine x, find the largest error of a third degree polynomial and use it to approximate f of 0.4. Well, cosine x is alternating, so I'm guessing that x cosine x minus x is going to be alternating. So I'm just going to generate this series without using, I'm going to use it, go off of our memory from cosine x is going to be, let's see, 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. We'll do one more. Right, so then let's see, x cosine x, multiply everything by x, oops, and then we subtract x. Well, that gets rid of this first term is gone, so we just have negative x to the third over 2 factorial plus x to the fifth over 4 factorial minus x to the seventh over 7 factorial. Okay. We're trying to find the error of a third degree polynomial. Well, that would just be a one-termed polynomial approximation, and we're using it to approximate f of 0.4. So again, this is alternating. We are just going to take the fifth term, or the fifth degree term, because the fourth degree term will vanish. And so we know the error is going to be less than the absolute value of 0.4 to the fifth over 4 factorial. Okay. And next one. So again, pause this, try it on your own first, then come back to it. Okay, so e to the 2x is not an alternating series. We are trying to find the error bound for a third degree Maclaurin approximation. Third degree. So we need to find the fourth derivative of x. Okay, our center is 0 because it's Maclaurin. Sorry about my messiness here. Wow, this is really messy. Let's do this again. Okay, so we're trying to find the fourth degree, or the fourth derivative. Let's see. Every time I derive, I have e to the 2x times some guts of 2. So the first derivative will have 2e to the 2x. Second derivative will have 2 times 2e to the 2x. Third derivative will have 2 times 2 times 2e to the 2x. And the fourth derivative will have 2 times 2 times 2 times 2, 2 to the fourth e to the 2x. And I'm trying to find the largest value between 0.2 and 0. And so it's looking like 0.2 is going to be the largest one. So f prime of 4, I'm sorry, f, the fourth derivative of 0.2, 2 to the fourth times e to the 0.4. Okay, my error then will be less than, let's see, 2 to the fourth, e to the 0.4, we're going to have x x to the fourth over 4 factorial. So 0.2 to the fourth over 4 factorial. And I do not have my calculator right here at this point, so I'm going to let you figure out what that number is. Okay? All right, that's not a 0.2, that's a times, yeah, it is a 0.2 to the fourth. Sorry about that. Okay? All right, next one. Cube root of x, centered at 1. Oh, we finally have one that's not centered at 0, so our center is 1. We are going to plug in x equals 1.3. And let's see, second degree Taylor polynomial, so we are going to use the third degree. I keep saying to the degree, the third derivative at some value c. We'll figure out what that is in just a second. And we are looking at x minus 1 cubed over 3 factorial. So in for x, we are going to put this 1.3. We're going to see about c in just a second. So let's get our derivatives. So the first derivative, 1/3 x to the negative 2/3. The second derivative, oops, negative 2/9 x to the negative 5/3, and the third derivative, 10, we're looking at 10 over 27 x to the negative 8/3. All right. So let's see. We are going to have to figure out whether we plug in 1 or 1.3 to figure out which one gives us our largest derivative. So, well, let's remember that 10 over 27 x to the 8/3. That 8/3 will go in the denominator because of the negative exponent. So if I put 1.3 in here, that's going to make the denominator larger, which will make the fraction smaller. So I actually want to put 1 in here. That will make the denominator smaller, which will make the fraction larger. Okay, so I'm going to use 1 in here. So my error is less than. Okay, I'm putting 1 in for, that's like, so my c value that I'm plugging in for my derivative is 1. We found that that's going to give me the largest derivative, third derivative. So if I put 1 in here for x, I'm going to get 10 over 27. And then in for x, I'm going to put 1.3 minus 1 cubed over 3 factorial. Okay. Oh, and you know what? That makes sense too, that 1 would be the best one, because this series, because of the derivatives, end up alternating. So we could just go to the next term anyway, which would be this. Okay, which would be if we plugged 1 in. So hey, it's cool how that works out. And again, on an AP test, you will have to use your calculator and figure out what that is in to the nearest third decimal. I'm gonna let you do that on your own. Okay, and the last one, we are centering it at 1. We're looking at natural log of 1.2. Oh, this is different. What degree Taylor polynomial? So we are going to have to figure out what degree we need to use so our error is less than 0.001. Okay, so I stopped the recording a little bit and played around with this just to see what we have to do. So I'm just kind of using a trial and error method. I did these derivatives here and I realized that derivatives are alternating, which means we're centering this at 1. So when I plug in 1 for all of my x values, well, after our first derivative, it'll alternate, but eventually our series is going to alternate. It should be negative here. And this is -6. Sorry about that. So I just messed around here, and I figured out the error bound for a secondary degree polynomial. So I went to the third degree, and that's what I'm doing here, is this third degree error bound. And so I ended up with the third derivative at 1, which was -1, and then times 0.2 to the third, because it would be x minus 1, centered at, the series is centered at 1, so x minus 1 to the third. 1.2 minus 1 is 0.2 to the third, divided by 3 factorial. So I ended up with this, and that's 0.0013, which is not quite small enough. So that tells me I've got to go to the next term. So let me just, I'm going to get rid of this, and I'm going to go to the fourth degree term and see what I get for that. So here we go. We've got the fourth derivative at 1. And remember, this is alternating, so I can just plug in my center will always work for my largest derivative, my largest fourth derivative. And then I'm going to have 1.2 minus 1 to the fourth over 4 factorial. Yeah, I'm pretty certain this is going to work. So we've got 6, that's my fourth derivative here, times 0.2 to the fourth, all over 24. So real quick, let's just work that out. We've got 6 times 0.2, oh brother, there's no exponent on this calculator. So let's say 0.2 to the fourth would be 0.000, oh no, 0.0016. I believe that's right. 2 to the fourth, 2 times 2 is 4 times 2, and move it over 3. Yeah, so we're good there. Times 6. And we're going to divide that by 24. And I get 0.004. Whoops. Phew. 3 zeros on a 4. Okay, which is less than 0.001. So that tells me, since the fourth degree term gives me a number that's less than 0.001, that means I have to use a third degree Taylor polynomial series to have an error that's going to be less than 0.001. So our answer here is third degree. Hopefully that makes sense. And if you come up with a better way other than trial and error, we'll talk about it in class. Okay? That's it. I think we went through all the examples, so let me just double check and make sure. Whoa. Whoa. Yep. Okay, I'm going to turn off the video now and see you in class.